Final speaker of the day is Chris White, who's going to tell us about the classical double copy.
Well, thanks for the invitation to be here indeed. It's nice to always be back in Cambridge. So this is going to be a talk about the classical double copy. So let me start by roughly saying what the double copy is, although this is a fairly expert audience. But the double copy relates perturbative amplitudes in gauge and gravity theories. So when I say gauge theory in this talk, I mean something like QED or Yang-Mills theory, an abelian or non-abelian gauge theory. Gravity is, of course, a kind of gauge theory, but I have to draw some distinction between the two types of theory, so I'll call them gauge and gravity theories. So the double copy is some relationship which is purely perturbative between those two theories. So I can write a very general form for an amplitude, and let's say it has m points and L loops. And let me write a form for that in a gauge theory. So it'll have some powers of the coupling constant, and then a sum over cubic graphs, I. Then there will be integrals over loop momenta. And there'll be various things like symmetry factors for each graph. And then finally, where the sort of meat of each term is, there's going to be a color factor for each graph, and the denominators, which may, for example, come from propagators. And then finally, there is this factor here, which is everything else. So in each term of the amplitude, you have a kinematic numerator that contains dependence on momenta, polarization vectors, and so on. So this is a kinematic factor, and this is color. Now, if anyone has not seen this before, you may think, well, why are we only summing over cubic graphs? We also have 4 gluon vertices and things in the Yang-Mills theory. I can always choose to rewrite 4 gluon vertices in terms of pairs of cubic vertices, so we can restrict ourselves to sums over cubic graphs only. So with that very general form for an amplitude in gauge theory, what the double copy says is if you replace this coupling constant of the Yang-Mills theory with kappa over 2, where kappa squared is proportional to the Newton constant, and if I then strip off these color factors and put in a second set of kinematic numerators, that automatically becomes a gravity amplitude. So the double copy, first of all, let me say, is not manifest in arbitrary gauges. We need these numerator factors, Ni, to satisfy something called BCJ duality. So this explains why this thing was not noticed until relatively recently. It's only if you write these kinematic numerators in a certain form, and you can do field redefinitions and gauge transformations to get them in that form, then if you have an expression that obeys that sort of relationship of BCJ duality, which I won't really go into what it is, then you can take this double copy to gravity. Now that explains, that suggests that there is some deep connection, possibly, between gauge and gravity theories that hasn't been noticed before, and that's why many people in this room, of course, have been working on this, because it's potentially a very exciting idea. Now, related to it, there's something called the zeroth copy. So what I did there was take off the color factors and get something with 2 lots of kinematics, and which gravity theory I get depends on which gauge theories I chose to take these kinematic numerators from. I could also have taken off, if I go back to my original expression in the gauge theory, I could have taken off these kinematic factors and replaced them with a second set of color factors, which again may have come from a different theory. And that's called the zeroth copy, because it's kind of the opposite of doing the double copy. And this gives us an amplitude. So it gives an amplitude in what's called a biadjoint scalar theory. So let me define this theory just by giving its field equation. It contains a field which is scalar, and it has two adjoint indices. So the full field is this contracted with two sets of color generators. So it would be some phi, which was matrix valued, is phi AA prime TA T tilde A prime, so in principle two different Lie algebras. The field equation of this is a kinetic term and then minus a coupling constant y and two sets of structure constants and a product of fields, so it looks like this. So there's a nonlinear term there which is quadratic in the fields, and thus it's a cubic theory in terms of the Lagrangian. Now, such theories are quite novel and interesting. As far as I know, they haven't been studied in great detail before, but they have started to occur in lots of different places in the literature. So they're there in the double copy literature. They're also there in the CHY equations. You can take a sort of zeroth copy, and that takes you to a scalar theory, which is a biadjoint theory. Now, one of the reasons these are interesting is that this BCJ duality that I talked about is manifest in this theory. So what this BCJ duality is it tells you that every time you have Jacobi identities for the color factors of graphs in gauge theories, you have accompanying like Jacobi identities for the kinematic factors. Here we have a vertex, a cubic vertex, that manifestly involves two sets of structure constants. So any set of graphs you write down will obey two lots of Jacobi identities. And so that's why BCJ duality is manifest in this theory. And that's what makes, or one of the reasons that makes these theories interesting. So one of the applications of them in the literature has been to look at amplitudes in this theory and to use them as building blocks for amplitudes in gauge theory. So we can use biadjoint amplitudes as building blocks for gauge theory numerators. And that's the only point I want to make about these theories for now, which is that properties of these biadjoint theories are somehow underlying gauge theories. And then because there's a double copy relating gauge theory to gravity, there's somehow underlying gravity as well. And we'll see that idea occurring at least twice more, I think, throughout the talk, that in principle one could use further properties of these theories as building blocks for more complicated theories. So just as a bit of further motivation, the double copy is conceptually interesting in that it relates to very different kinds of theory, but there might also be practical applications. So I'll put a question mark there because not all of them have been realized. But for example, there are various cases where we have to calculate even just classical gravity amplitudes. One example would be in gravitational waves. Another example would be in cosmological perturbations, so amplitudes on a curved background. And if it were possible to do simpler calculations in a gauge theory and run them through the double copy, that would simplify those calculations. So there are sort of, 4 branches of the archive, GRQC, AstroPH, HepTH, and HepPH, that can all get unified by this set of ideas. Now, if this thing is really true, if there really is a link between gauge theories and gravity, then one might hope that it goes beyond just perturbative amplitudes. So these perturbative amplitudes are at fixed order, and we might say, well, can we actually take all order results, either perturbatively or otherwise? And very optimistically, we might hope that there's some non-perturbative manifestation of this. then that would really tell us that there was a link between these theories, and it also might help explain where the double copy was coming from. So if it is really true must be possible to match exact solutions. Now, there are two types of exact solution that I can talk about. Yes?
Right. In the bi-adjoint scalar, is the potential positive definite?
See, naively one would think...
If it's not, then, I mean, non-perturbatively, it's a sick theory, right?
Well, naively one would think it's cubic, and therefore the energy would be unbounded. But if you actually put in anti-symmetry conditions on here, I don't know whether it's always true that the energy is, for every solution, unbounded. The other thing is that what happens in both perturbative amplitudes and in the classical double copy that I'll talk about is that you don't really care whether the vacuum is stable or not. It just is true that solutions of that theory propagate into other theories where the energy is well defined. So you kind of don't really care whether the bi-adjoint theory is physical by itself if properties of that theory somehow are there underneath gauge theory and gravity solutions. I mean, I don't think anyone's claiming that this theory is directly applicable to nature by itself.
Well, I'm not talking about natural necessarily. I'm just saying, that the potential is unbounded from below in a sense.
Well, again, that doesn't seem to stop bits of that theory propagating into other theories. So something that may be unphysical in this theory becomes physical, if you like, once it gets stressed in other theories. So yes, there are two types of exact solution one could talk about, perturbative and non-perturbative ones. So I will talk about the first case first. So the basic idea is as follows. Step one is to find a graviton, h mu nu, and all of the ones I'll talk about in this talk are deviations from Minkowski space. So, well, there's a factor of kappa I've ignored there, but this is just schematic. So we want to find a graviton field h mu nu and a gauge field a mu such that the graviton is some sort of product of the two gauge fields. It may not be as simple as that, as we'll see, but that's the basic idea. So that's why this thing is some sort of double copy of the gauge fields. But then we also want to argue that that's a manifestation of the same double copy that's underlying perturbative amplitudes. So the second step has to be show that, or I'll just say show this is the same as BCJ, which is this double copy for amplitudes. So the starting point for this are things called Kerr-Schild metrics. So these are very special solutions in general relativity, which for those with backgrounds in general relativity, they may know about these already, but I'll assume they're not generally known. They have a very special form where h mu nu is equal to some scalar field phi times an outer product of some vector with itself. So this can't just be any vector. It has to be null, and it has to be geodetic, meaning k dot d k mu is equal to 0. So these are well-known solutions going back decades. But the reason those solutions are very special is because you can show that they linearize the Einstein equations. So that's quite remarkable, especially if you've not seen this before. A remarkable fact is that the Einstein equations become linear. So just as an example, I can give you the Ricci tensor on just general grounds. If you just make these assumptions on K, if I put one index up and the other one down, then I get a half, and then d mu d alpha phi k alpha k mu plus d nu d alpha phi k alpha k mu minus d squared phi k mu k nu. Now the details of this are not at all important, of course. The only thing that matters here on the right hand side for what I'm saying is that this is indeed linear in that graviton. Now it is actually, there's a caveat to this. The equations are only linearized for this particular index placement. However, if we stick with that index placement, one up, one down, then we can show that these are exact solutions of the Einstein equations, and that's important. It means we don't have to worry about going to further orders in kappa. We have an exact solution. So the implication of this is that these Kerr-Shield solutions are exact. So we've got part of the way then to fulfilling step number one, which is to find an exact solution which we can use to possibly set up a double copy of exact solutions. Now we have to find the gauge field, but because of the form of this, it does suggest a reasonable guess. We want something with one Lorentz index, and so it suggests we just take one of these vectors off, and we look at the thing that's left, and we ask, is that a sensible gauge field? So given the form of h mu nu, guess a single copy so this will be a gauge field now, living in a different theory, and it is in principle Yang-Mills theory, so there'll be an adjoint index there. And I'll call that Ca phi k mu. So what I've done is dress this with just some arbitrary color vector to get a non-abelian result. So this is, I'll just put arbitrary color vector. And then we can ask, well, is this a sensible gauge field? Well, the answer to that question means if I plug this into the Yang-Mills equations, does it solve them? And in fact, you can prove the following. So can then show for all stationary Kerr-Shield solutions that d mu f mu nu a is 0, where f mu nu a is the usual field strength tensor. So it's d mu a nu a minus d nu a mu a. So what we find then is that at least for stationary solutions where there's no explicit dependence upon the time, this single copy is indeed a well-defined gauge field. It satisfies the Yang-Mills equations. But something else has happened here. This is a field strength tensor for an abelian theory. So these are the Maxwell equations, which are what the linearized Yang-Mills equations are. And that's perhaps not surprising. We started with something that was a solution, it was an exact solution, but it was a solution of the linearized Einstein equations. And we've ended up with a solution then of the linearized Yang-Mills equations. So these are the linearized Yang-Mills or Maxwell equations. So this is nice because it does tell us that there's an infinite class at least of exact solutions in GR of which one can take a single copy. So this is an infinite class of exact solutions. And in fact, well, what I really want to say is it's an infinite class of classical double copies. However, those that have been watching carefully will notice that there's an ambiguity at this point, because I said, well, I'll just take off one of those vectors k, and then I'll get something, and I'll call that the gauge field. But that procedure was ambiguous, because what was to stop me, for example, absorbing some of this function into the k's, for example, the square root of phi or something, and then taking the vector off. So there was a kind of ambiguity in a position-dependent factor that I could have absorbed into these vectors before I took the single copy. We might ask, well, what actually is it that fixes that ambiguity? So I'll just put here, however, the procedure looks ambiguous, and the question is, what fixes phi? Now, in fact, the answer to that question turns out to be the 0th copy. So if I follow the same procedure of stripping off one of these k vectors and adding an arbitrary color vector, then taking the 0th copy by that same result, I'll get a field which has two adjoint indices, a scalar field, and two of these arbitrary color vectors, but sitting in different theories now, so associated with different algebras, times this same field phi. And I can then ask, what is that the solution of? And in fact, you can show from this, if it's a well-behaved phi, that it satisfies d2 phi is 0. So in other words, this is the linearized biadjoint scalar field equation. So that gives us the answer to what fixes this ambiguity. If you look at the biadjoint scalar field theory, for phi to be in one of these classical double copies, it has to be a solution of the linearized biadjoint field equation. And I've not bothered writing source terms here, but if there were source terms, they'd be on the right-hand side in all the theories. So this isn't necessarily the vacuum equation that I write down. But phi is a solution of that equation. And there's another way to think about that. Well, first of all, actually, let me write that point. So for the double copy to work, phi must solve the linearized biadjoint theory. Now, there's another way to think about that, which is that a solution of that equation is a scalar propagator, because that equation is an equation for a scalar propagator. And that's exactly the same as what happens in the BCJ story for amplitudes. In the BCJ story for amplitudes, you touch the numerators, or the color factors. So you look at the numerator of the expression and you play with the numerator and replace color factors with momentum factors and so on. You don't touch the denominators, you leave them as they are. Now those denominators are scalar propagators. That's all they are. So indeed, this is, if you like, the same procedure. So i.e. phi is a scalar propagator, which is the same as BCJ. So that really goes a long way towards fulfilling number 2, or step number 2 that I wrote over there. Now I should say that there is more evidence that I don't have time to talk about here for this procedure being correct. So existing results in the literature, for example, papers by Ricardo and Donal about self-dual amplitudes, those can also be expressed in this Kirchhoff language, albeit in momentum space rather than position space. But again, that tells us that this procedure is really intimately related to the BCJ double copy. Well, it's some sort of manifestation of the same thing. So after that rather abstract discussion, let me give a couple of examples. One that perhaps people know and love. I mean, what motivated me certainly, and probably the others to first look at this, was what, for example, is the single copy of a black hole? That would be an interesting thing to find out. The square root, if you like, of a black hole. And the simplest solution, black hole solution you can think of, is a Schwarzschild. Now that in this Kerr-Shield language, it does have an own Kerr-Shield form. The field phi is given by m over 4 pi r, where r is just the radial distance, and k mu, this Kerr-Shield vector in that case, has 1 in the time-like direction, and for the space-like bit, it's a unit radial vector. And so if you take the single copy of that, you get a field A mu, which is, it'll have this arbitrary color vector, and if I want the field, I then have to contract with the actual color generators to get the matrix valued Yang-Mills field. I divided by 4 pi r and just times this, this vector. So I may want the mu downstairs there, but whatever. And that perhaps we don't necessarily recognize, but it's fairly straightforward to do a gauge transformation of that and show that it becomes the following. So then you get that A mu is G CA over 4 pi r, and then 0 for the space-like bit. So I've been somewhat crafty here in the sense that I have replaced m with this combination of charge, and I've replaced kappa, or rather kappa over 2 in the gravity theory as it turns out, with g as some coupling constant of the Yang-Mills theory. Now those are the usual BCJ replacements that one would do, replacing momenta with color charges and coupling constants with factors of 2. And then what I get exactly is the Coulomb solution. So this is a static color charge sitting at the origin. What's nice about this is that indeed factors of 2 and everything work out. It really is true that the BCJ replacements that you would make for an amplitude when applied to these exact solutions give you the Coulomb solution with exact factors of 4 pi and so on. Now this is quite an interesting result by itself, because I think we first suspected when we were looking at this that a Schwarzschild black hole, if you write it in most choices of coordinates, actually goes to all powers in the gravitational coupling. So it's an infinite series in the gravitational coupling. And so we strongly suspected that it would be some completely non-linear, non-abelian object, like a monopole or something, that would copy to give a black hole. Here we see that's not true at all, in fact. It's an abelian-like point charge sitting at the origin that can give you a black hole. But there's a word of caution here that that's not to say that there couldn't be a non-linear thing that also copies to give you a black hole, because you strip off color factors when you do the double copy, and information in that sense gets lost. But it seems to imply that if you did have, in some other gauge, for example, a non-linear result for something that copied to a black hole, you could somehow gauge away that non-linearity to leave you with a simple abelian-like result. And there's some papers by, I think, Sickerby and Weiss in the 70s that suggest that that's the case. So a second example I will give, just because some people at least like black holes, that's a Kerr solution. So that has a phi field given by, and for some reason here I've included explicit factors of the Newton constant. But you have some field phi which goes like 2mg, which is Newton's constant, r cubed over r to the 4th plus a squared z squared. And a vector k mu, which is 1 in the time-like direction, and then some fairly abstract looking thing in Cartesians. But let me explain what these things actually are. R here is the spheroidal radius. So we're in spheroidal coordinates, which live on a squashed sphere. And this is the 3 direction is some spheroidally radial vector. So it's pointing out in the radial direction of that squashed sphere. Now what the Kerr black hole is, for those that don't know, is it's a rotating black hole. So it's the simplest solution we know for a rotating black hole. And it has horizons associated with it that are spheroidal rather than spherical, hence the reason that this is a good coordinate system. Now this parameter A here is related to the angular momentum. So this actually, as you can see, has dimensions of length, but it's related in principle to the angular momentum. So that as A goes to 0, the angular momentum goes to 0, and in fact you then recover the Schwarzschild result, which is above. So So this is a rotating black hole. And you may ask what the source for that is. So the source for a Schwarzschild black hole can just be a point mass at the origin. Here you need a more extended source to source the rotating black hole. You need something with a structure to be able to have that angular momentum associated with it. So this is a rotating black hole sourced by a rotating mass disk. So if I draw in the XZ plane, well, there's sort of Y coming out, and then you've got this basically very thin disk of stuff, and there's a certain mass profile on that disk, and it's rotating about the Z-axis. That actually gives you the source for the black hole. And then if you take the single copy, I won't bother writing down the expressions because you can just get them from this, but it doesn't really tell you what the thing is. If you take the single copy gauge field and ask what actually is it, well, it turns out to be a rotating disk of charge. So exactly as in the Schwarzschild case, the mass gets replaced with charge, and the exact profile of the mass, the density profile of the mass on the disk, gets replaced with the same density profile of charge in the gauge theory. And then you can do things like plot electric and magnetic fields. So single copy is rotating disk of charge. And if I were using slides, I could show you some nice plots with mathematical of these magnetic fields. The one that's easiest to draw and is the easiest to understand is actually if you look at large radial distance. So e.g. the magnetic field at large r. So if I have the disk is sitting in this plane, but I've really zoomed out from it, so it would be very small down here, then I get something that looks like this. So this is meant to be nice and symmetric. But that is basically the magnetic field of a bar magnet. And it wasn't a surprise, of course, when we saw that, because a rotating disk of charge is a series of coils, and coils are solenoids. They're bar magnets, essentially. So if you zoom out, then this is exactly what you should see, which indeed is the case. Now, there is a bit of a subtlety here, which I haven't really got time to go into. But it turns out that the sources in these theories are not exactly related by some sort of double copy procedure. Now, there's no reason why that necessarily has to be the case. What the double copy says is the fields themselves should be double copies of each other. The sources are extra degrees of freedom that you put into the theory just to give you the right fields. What we found is that the source, indeed, in the electromagnetic theory is just a rotating disk of charge. In the gravity theory, it's a rotating disk of mass plus extra terms that are needed to stabilize the disk. So the point is that like charges repel in gauge theory, but they attract in gravity. And so you need somehow some extra radial stabilization terms to actually make sure the disk doesn't collapse in gravity. And that's because we've presumably asked for a stationary solution, so that had to happen. Now, there is an interesting recent paper by Mark Wise and Alex Ridgway where they look at sources in more detail and what the implications are. So if anyone's interested, then that's quite a nice paper to read. And just as a throwaway comment, higher dimensions also works. Now again, BCJ for amplitudes is not tied to any particular dimension. And it's exactly the case here. So strictly speaking, for Schwarzschild, it's a Tangalini black hole one is talking about in higher dimensions. And the Tangalini black hole indeed matches up. And then the higher dimensional generalizations of the Kerr black hole are the Myers-Perry black holes. And those work as well. So that was the first story that we came out with. It does fulfill both of those conditions above, that we have this family of classical double copies. We've argued it's the same as BCJ. What we'd like to do now is kind of go beyond that simple case that we can do, because these solutions, infinitely various though they are very special. They're stationary, and they're this particular Kerr-Schild form. Now, one consequence of that is that because the graviton involves an outer product of a null vector, the trace is 0, and the antisymmetric part of that thing is 0. So that means that we're not sourcing the two-form or dilaton, which would normally be required by the double copy. So it'd be nice to see solutions, for example, where those are present. But we have got some cases where we can go beyond this simple story. So we can go beyond stationary Kerr-Schild in two main ways. The first, given we looked at stationary solutions, whoops, that's no longer stationary, is time dependence. And there are some cases of this, in fact, that are known in the literature already. So one that is known to work is plane waves, including non-abelian plane waves. Non-abelian plane waves were first arrived, I think, by Coleman in the 70s. And I think it's an exercise in Warren Siegel's Fields textbook that you can show that those match up in gravity and Yang-Mills theory. And also shock waves also match up. They're in this Kerr-Schild description. So, I mean, both of these in some way are kind of solutions where k is pointing along the light cone. So there is some time dependence, but it's a rather trivial time dependence. And then they fit in exactly to this Kerr-Schild story. But that's nice, though, because it also bolsters the fact that this is equivalent to the BCJ story for amplitudes, because shock waves have also been looked at recently by Akuri and Sautomi, who actually summed Feynman diagrams to all orders to generate a shock wave and used the BCJ double copy for those amplitudes to show that the shock waves had a double copy. So whether you get it from Kerr-Schild or whether you get it from Feynman diagrams, it is the same result. Now, the other thing one can do here is go to multi-Kerr-Schild. So I haven't got time to spell this one out in detail, but I'll say a few words about it. Multi-Kerr-Schild just means you have more terms of this form. So you would add a second term here, which was some psi of x, L mu, L nu, where L obeys similar conditions to that, and there are mutual conditions between k and L. There, you're not guaranteed to linearize the Einstein equations anymore. So they're useful for various other reasons, these multi-Kerr-Schild solutions, but they don't necessarily linearize the Einstein equations. It's very complicated to show that they do. Remarkably, in some cases, that multiple Kerr-Schild thing does linearize the Einstein equations. One of them is the Taub-Nutt solution. So this is something where the gravitational field has a Schwarzschild-like bit, but also a sort of contribution that is non-trivial at infinity. It has a rotational character associated with it. And in fact, for Taub-Nutt, the single copy is a dion. So it's a static point-like particle in a gauge theory that has both an electric charge and a magnetic monopole charge. And under the double copy, the electric charge becomes the mass, as it did in the Schwarzschild case. Now, this is the equivalent of taking a form momentum or a kinematic thing and replacing it with a color generator. If you take a static form momentum, which is kind of like a mass, that would become a sort of static charge in the gauge theory, the usual double copy story. Then it has a magnetic monopole charge, and it's that becomes the Nutt charge. So that's the name of this thing in general relativity that can give your gravitational fields a rotational-like character. Now, this is not entirely new in the sense that there has been an analogy before in the literature saying that Taub-Nutt solutions are a bit like magnetic monopoles, but for gravity. And that's always been an analogy, and people have sort of said, well, if you look at large r, which in most gauges is where it simplifies only at large r, but say, well, at large r, it sort of looks like a magnetic monopole. This is an exact relationship. It's exact because it's Kerr-Schild, and so it's linear solutions. They exactly solve the Einstein equations. And you really have an explicit relationship between a dion in one type of theory and a Taub-Nutt solution in a gravity theory. Now, there's one other case of time dependence that I can mention. So we wanted to really go beyond even this. And perhaps the simplest case of time dependence that you can think of is an accelerating particle. So we don't have to worry then about extended sources. We can look at a point-like thing that's arbitrarily accelerating. And there is a known Kerr-Schild form for that. So phi here is m over 4 pi r. I'll say what r is in a moment. And k mu is some x minus y mu divided by r. So we'll draw a picture to say what all these things are in a minute. But this r now is the retarded distance rather than just the radial distance. So it does have a time dependence then associated with it. So what we have here is a particle following some world line. And then at some point on the world line, let me get this right, that is y, we can draw a light cone. And then I have the point at which I want to ask what is the field at that point. And that's the point x. And then that distance there, or that vector along the light cone, is the Kerr-Schild vector. And then the retarded distance is, this sort of retarded distance, if you like, the invariant distance that takes you back to this point on the world line. Now you can plug that into the Einstein equations and ask what you get. This has been done before because these solutions have been known since, I think, the 70s or so. And you get something interesting in this case. You get non-zero source terms. So when you plug this solution into the Einstein or the Maxwell equations, if I take the single copy or the double copy of the thing, we get non-zero source terms. So in the Maxwell equations, you end up with a current on the right-hand side, which is the source in the gauge theory. So I'll call that J mu Kerr-Schild. And it turns out to be 2g over 4 pi k dot lambda dot over r squared k mu, where everything is evaluated at the retarded time, and lambda is just the tangent to the world line. So this is proportional in some sense to the acceleration. And then in gravity I get something that looks like T mu nu Kerr-Schild is 3m over 4 pi k dot lambda dot divided by r squared k mu k nu, where again everything is evaluated at the retarded time. So for the other solutions that I talked about, Schwarzschild and Kerr, they were basically vacuum solutions up to some delta function source on the right-hand side of the Maxwell or the Einstein equations. And that was the point-like source that sourced the fields. Here there's also such a point-like source localized on the world line, which I've just not bothered showing. But what I'm saying is you also get these non-zero source terms that are actually defined at any point in the space. And that looked very mysterious when we first saw it. But in fact, one can interpret these as follows. So first let me define something which I'll call a radiative gauge field, A mu rad, as, so I'll look at the gauge theory case, and I'll define that to be g over 4 pi r lambda mu minus k mu. I don't know why I'm really bothering to say exactly what this is. The only point about it is that you can then show that if you form the field strength tensor for this object, you get minus J nu Kerr-Schild. So if you plug the normal Kerr-Schild solution into the Maxwell equation, you get this plus J on the right-hand side. If you were to plug this thing in, you get minus J. So in other words, the sum of the two things is a vacuum solution up to this point-like source term. And in fact, if you ask what actually is the sum of them, then A mu, the Kerr-Schild bit, plus the radiative bit, is proportional to lambda mu over r, which for those that recognize their electromagnetism is the Liénard-Wiechert potential. So this is the known exact solution for the field due to a accelerating radiating particle in electromagnetism. And what the Kerr-Schild story has done is that it somehow insisted that the boosted Coulomb part is on the left of the Maxwell equation and that the radiation part is on the right. So the radiation is encoded in this. It goes like 1 over r squared, for example. And the rest of the solution, so this Kerr-Schild solution itself, must correspond to the boosted Coulomb part only. And indeed, you can show that that's the case. Now, another way of saying that this must have something to do with the radiation is that it's proportional to the acceleration. And it's only an accelerating particle, of course, that can radiate. So there's a similar story there in gravity, which is more or less the same as the electromagnetic one. But this also allows us actually to make a link with BCJ in a bit more detail. So we can also link this to BCJ. The Maxwell equation, if I actually write it down for the field, is basically an inverse propagator times A mu is equal to J mu. I mean, the definition of the propagator is the inverse of that quadratic operator that acts on the left-hand side of the Maxwell equation. Now, if we compare this with the LSZ formula in quantum field theory, you know, what you're meant to do, of course, for external lines is truncate the propagators on them. And that basically tells us then that epsilon mu J mu Kerr-Schild is the amplitude for photon emission from a particle. In other words, what this is it's the field produced when a particle gets, or when a photon gets radiated off a particle, and that is an off-shell photon that's been radiated from a particle. If I truncate the propagator, LSZ tells me that that should now be an on-shell photon, and thus, if I take whatever is on the right-hand side here and I contract it with a polarization vector, that must be the amplitude for photon emission from a particle, and similarly for the gravity case. Now, we looked at this explicitly in the Bremsstrahlung limit so that's where the particle, I'll take it as having some full velocity u mu, and then suddenly there's a kink in its Wode line, so it accelerates rapidly in a short period of time to some second full velocity u prime. And if you Fourier transform things into momentum space, which is where we would normally recognize amplitudes, so I'll put tildes on the currents, then epsilon mu J mu turns out to be minus Ig epsilon dot u prime over u prime dot k minus epsilon dot u over u dot k. And epsilon mu, if I take a polarization tensor for the graviton, times this Kerr-Schild energy momentum tensor in the gravity case, I get minus I m, and then I guess a kappa over 2, and I get epsilon mu u, u prime u over u prime dot k minus epsilon mu nu over u dot k. So that's a bit of a mouthful. But the point is, these are known things. So if you haven't seen them before, take my word for it that they're known things. This is the known amplitude, what we call the iconal amplitude for Bremsstrahlung of soft photons. This is the known iconal amplitude. You can look in Weinberg's paper, for example, in 1965, for soft gravitons. So there we see an explicit link, indeed, between what's going on in this Kerr-Schild double copy, or the classical double copy, and known amplitudes, which satisfy the BCJ double copy. So, well, the point I guess I want to make is that the Kerr-Schild double copy is BCJ. So that's how exact solutions can work in the perturbative sector. Now, even though they're exact solutions, and even though we haven't gone to higher orders in perturbation theory, they're still, in a sense, perturbative. So they depend on positive powers of the coupling constant. And essentially what a Kerr-Schild solution for a given metric is a resummation, to use a sort of QCD term, of metrics in other gauges. So if you were to take the Schwarzschild solution in a normal gauge, it would go to all powers in the gravitational coupling. However, by doing some kind of resummation, by gathering up all the terms in a different way, you can actually put it into a single term. and such things happen in QCD pheno and things a lot of the time. So that's still a perturbative result. And it would be nice to know whether we can go beyond perturbation theory. I should say there's still a lot to do in perturbation theory, so these are still very special solutions and we'd like to go beyond them. But can we go beyond perturbation theory? And it's easy for me, at least, to answer that question. I have no clue. I just don't know if we can go beyond perturbation theory, whether it's possible, how one would do it. Now, the reason is that it's difficult even to think about is that in both the BCJ double copies and this classical double copy, phi, this field in the classical double copy, or the denominators in the BCJ story, those were solutions of the linear biadjoint equation. So they're solutions of the linearized scalar theory are playing a crucial role. As soon as you go non-perturbative, you don't have that sort of crutch to rely on. So it's not at all clear how you would do this. However, it's worth thinking about, of course. Now, if this were really true, if it was some non-perturbative thing, then optimistically it may explain the origin of the double copy. At least tell us some underlying reason why it has to be there. Now, we have some intuition, of course, from string theory and so on, but again, that's perturbative, and it's only at tree level in that case. And, well, possibly loop level generalizations as well in ambitwistor string theory, but it's not a complete explanation. So, despite saying I don't know how to do this, I think the first step in doing this would be to say, well, in the perturbative results, it was solutions of the biadjoint field theory that acted as building blocks for what happened in gauge theory and gravity. Let's hope that that's the case in the non-perturbative sector. So let's say that what we'd like to be able to do then is at least find some non-perturbative solutions for the biadjoint theory, and then hope that they might be used as building blocks for things later on if we can figure out how to do it. So recently, I have found some solutions. So I'll just put them here as sort of food for thought, and there's a bit of fun to end with. So recently I have found solutions. And these are restricted to particular cases. So there's one where you can look at the case where, perhaps it would help if I wrote down somewhere the field equation again. So the field equation I'm talking about is this d2 phi AA prime minus y FABC F tilde A prime B prime C prime phi BB prime phi CC prime is 0. I've looked for static solutions of this. Now the first one is if both of these gauge groups are the same as each other, so that these structure constants are equal to each other. And then I have something that goes like minus 2 delta AA prime divided by y TA r squared. So here, this is for FABC is equal to F tilde ABC and FABC FA prime BC is equal to TA delta AA prime. So that just defines this TA. This TA is just a normalization constant, which really depends on how you've normalized the color generators. And that solution has, if I think of these as being internal indices, that has spherical symmetry in that internal space. And what we can also see is that it does go like 1 over the coupling constant. So it is some non-perturbative solution, and it goes like 1 over r squared. So it's some singular thing at the origin, or some point-like thing localized at the origin. Now there's another solution if I restrict to the SU2 cross SU2 case. In that case, you can have mixing between space and color indices. And then you get something that goes like 1 over yr squared minus k delta AA prime minus xa prime over r squared, plus or minus the square root of 2k minus k squared epsilon a prime d xd over r. So that is for SU2 cross SU2. And here k is just some parameter that goes between 0 and 2 if you want the field to be real. So you can work out the energies of these things. The energy is well behaved as you go to infinity. It's singular at the origin, but that's exactly the same for an electron or something in Yang-Mills theory. It's a point-like disturbance at the origin. And they both have this dependence of being 1 over the coupling constant, 1 over r squared. This has cylindrical symmetry in the internal space. This has spherical symmetry. When you work out which has the lower energy, if you put an infrared, a UV cutoff in, a short distance cutoff, this has lower energy, presumably because it has more symmetry. Now, just as a pure piece of fruity speculation to end the talk with, I'll say that the possible things these might be related to in a gauge theory are Wu-Yang monopoles. So the Wu-Yang monopole is like a Dirac-style monopole, so a singular thing that's embedded into a Yang-Mills theory. And if I look at the SU2 case, then you can find a gauge in which A0 is 0 and AIA, so that's the space index, that's the color index, is minus epsilon IAK xk divided by ER squared. Or I can call that G, which is what I've called it throughout the rest of the talk. And for example, if I take this solution for k is 2, I can note that phi AA prime looks like a product of 2 Wu-Yang monopoles, where I have traced over the space indices, but left the gauge indices intact. Now you may say, well, this is normally how you would get a graviton, putting 2 products of gauge fields here, but then of course you would contract over the gauge indices and keep these intact, and we're in an SU2 case where the gauge and the colour indices are sort of on an equal footing. So with that piece, as I said, of quite fruity speculation, I'll end there. Thanks.
Questions for Chris?
What about solutions in ADS?
Oh, we haven't thought about that, although having said that, DS and ADS space have the Kershal description themselves. You can think about them as being deviations from Minkowski, where the sort of deviation from, which is not normally how you think about ADS, right? The deviation from Minkowski looks like, so the Kershal graviton in that case would be, it would go like lambda r squared, k mu k nu, where this is that same radial vector as in the Schwarzschild case. There's an r squared here, and lambda is related to the cosmological constant. Now that, if you take the single copy to a gauge theory and ask what actually is it, it turns out to be a constant charge density filling all of space, which is no surprise because it's a constant energy density, if you like, in the gravity case, and that's exactly what you expect the single copy to do. Now the fact that DS and ADS themselves can be written in this Kershal language at least suggests that in the Kershal framework it might be possible to use them in this multi-Kershal-like form to look at solutions which are in, instead of being about Minkowski, are about ADS. Because you already have some sort of Kershaldness about them that might allow that classical double copy to work. So I think Schwarzschild certainly does work in ADS. I think we checked that, didn't we? That, yeah.
I see. So then in that case, what prevents you from taking like a triple copy or a quadruple copy or?
Well, of course, when you do that, you need to have, oh, you see, you're saying in ADS you could have these high spin gauge fields, yeah. I would imagine that something could work. I mean, I've never tried it, right? But I don't know if anyone that works on these high spin theories has ever looked at triple copies or quadruple copies or something.
Well, I don't know, but I know of classical, I mean, black hole solutions and higher spin theories. They're certainly, I've seen papers with these words in the title.
I mean, I would guess that something there could work, and that would be worth looking at.
Right, and then I guess the other question, what about FRW type metrics? Are those Kershal at all? Or
well, the best person to ask is Andres, who's been looking at this.
I don't know. I have been looking for a form to describe FRW in a Kershal form, but I haven't found it. Only for the special case for flat FRW, which is the zeta. So yeah, when I tried to use an ansatz, the only solution I could find was the zeta. So if you have any lead on that, please tell me.
I should have, by the way, mentioned throughout the talk that Andres is on the papers. Andres Luna, who's here, and Izzy Nicholson, who is Daniel's student, is also on there. Yeah. Yeah.
Could you explain a little? I got lost by what you meant by Schwarzschild being perturbative, and these last guys you showed being non-perturbative. Could you?
Oh, it's just that Schwarzschild has positive powers of the coupling constant, right? So if you take the coupling constant to 0, if you take kappa to 0, Schwarzschild disappears and you're back with Minkowski.
Okay.
Here, if you take, you just cannot take what, this is a non-perturbative thing, it goes like 1 over the coupling. Something pathological happens as the coupling goes to 0, but that's of course if you were to start with the field equation and take the coupling to 0, you would never get that solution in the first place. So there's no sort of smooth limit in which you can take a
Perturbative around strong coupling?
Yeah, sort of, yeah.
Well, what would that gravitational solution, do you have an example of a gravitational solution that goes from?
No, I mean, I'd like to know how to do it. But as I said, I don't. But if you know, then we'd like to know.
Have we got anything else for Chris? Okay, well, let's thank this again.